All right, so I'm going to give you some motivation for the Magnus and Fer expansions, which show up in trying to, construct the group integrators. So this is motivation for Magnus and Fer expansions. So let's try to first start off by thinking about the simplest possible situation you could have, which are just scalar linear differential equations. So let's consider sort of the scalar linear differential equation. Okay, but I'm going to relax the condition that the it's like the equation is constant coefficient. So let's just say, for example, if y prime is equal to a of t y, right? And then t is greater than or equal to 0, and then y at 0 is y sub 0. Okay, so you probably know that this has a solution, which is can be expressed in terms of the integral. It's like of this coefficient a of t and some sort of exponential, right? So which has the solution y of t is equal to the exponential of the integral from 0 to t of a of t. Well, let's write this as a of cos c d cos c. All right, y0. Okay, so you probably, again, it's like we mentioned, that the exponential, of course, can be generalized to matrices. So you might ask whether the natural generalization of this provides a solution of the matrix analog of this scalar linear differential equation. So since the exponential can be generalized to matrices, right? It is natural to consider sort of this matrix exponential of the integral from 0 to t of some sort of coefficient matrix now a, cos c d cos c, okay, applied to y0 as a potential solution of the matrix analog of this equation, right, which is y prime is equal to a of t y, and again, sort of natural conditions, t greater than 0, and y at 0 is y sub 0. Okay, but the problem, of course, is that this is not going to be a solution unless you're in this situation where there's a certain commutativity, if you will. It's like of these A matrices, right? So, but this is not the solution. Right, unless basically the commutator of a t1 with a t2 equals to 0. So that means that these two matrices commute with each other for all t1, t2 greater than or equal to 0. And then, well, up to, if you were doing this just up some finite time, then of course, as long as this t1 and t2 were the interval from 0 to whatever that time is, then you would get that this was actually a solution up to that finite time. But if you wanted this to be a solution for all time, then it has to be that all possible combinations of these matrices evaluated at any time, it's like commute with each other. So that's an extremely strong condition. So this is not a solution unless this is true, and more or less has to do with the fact that it's like when matrices don't commute, it's like then you don't have the analog of e to the a plus e to the a plus b is equal to e to the a times e to the b, right? So you might have heard of the Baker-Campbell-Hausdorff theorem, and so that basically says that e to the a, it's like plus b is not equal to e to the a times e to the b unless a and b commute with each other. Okay, so so there's something analogous, if you will. It's like which has to happen. It's like if this holds true, and one way to sort of think about this is that this is sort of the generalization. It's like of a Baker-Campbell-Hausdorff type. It's like result. Okay. All right. So what can you do instead? All right. So you might ask. It's like first and foremost, it's like why is this a nice form? It's like to hope the solution it's like is in. It's like and if you can't do that, it's like how can you modify it so that you can still do something interesting? So the main motivation, if you will, is for studying solutions of this form is that if y is on a Lie group and a is in the Lie algebra, right? Then this equation here describes motion. It's like on the group, right? So y then is like a curve. It's like which lives on the group if y0 is in the group to begin with, and a is in the Lie algebra. Okay, so if you had that property, then of course if a is in the algebra is a vector space, so it's closed. It's like under linear combinations, and so this integral is still going to give you something which is in the Lie algebra itself. And then when you take the matrix exponential, that's going to give you something in the group, and when you multiply it with the initial value, which is also in the group, that is going to be the group. So more or less, it's like the advantage, if you will, of this ansatz for the solution is that it guarantees that this thing stays on the group. So this doesn't give you the answer you want. It's like, so the natural question to ask is, well, how do we modify it while still preserving this property that, it's like the candidate ansatz will stay on the group. Okay, and there are two ways to do that. So let me sort of just sort of summarize. It's like what I had just said, right? So what I basically said was that we would like to consider sort of corrections to this sort of matrix exponential of the integral from 0 to t of a cos c d cos c applied to y0. Which still sort of maintain the property that the ansatz automatically stays on the group, right? Group, let's call that G. Okay, and there are sort of two ways to do that. So let's think about what we had said. It's like to say that this automatically is on the group, right? So if we have something in the algebra and you exponentiate it, it becomes a group element, and when you multiply two group elements together, you stay in the group, right? So there are two possible ways to modify this. One of which is to add a correction factor to the algebra term, which is this integral term, right? So if we add a term which is still in the algebra, then again, when you take the exponential of that, it stays in the group, and then when you multiply it, you again stay in the group. Okay, so one possibility is to do a correction to this, all right? So one possibility is to introduce a correction. Let's call that delta of t, which is in the Lie algebra. Okay, and then consider solutions of the form y of t is the matrix exponential of this integral term, right, which comes from the scalar, or is motivated by the scalar solution, plus it's like this delta of t. Okay, and then apply it to y0. Okay, so that's one possibility, quite a natural thing to do. And then the other possibility you can have is that instead of mucking around with this term, you can try to mess around with this term, right? So as long as this term is a group element, then you're still okay as well. Okay, so let's try that. So another possibility is to consider a correction let's call that V of t now in the group, okay, with the property that y of t is the matrix exponential of the integral from 0 to t of a cos c d cos c applied to now v of t. Okay, and the point is that depending on which of these possible formulations of the correction you choose to the sort of the scalar-like solution or the scalar motivated solution, then you get two different expansions, if you will, for the solution. So these sort of lead to the Magnus and Fer expansions. Sort of respectively. Okay, so this is the one which is associated with Magnus, and then this is the one associated with Fer expansions. Okay, so that's at least some motivation, if you will. It's like for how one might set up. It's like these Magnus and Fer expansions. So the next thing I'll do is to actually talk about what exactly you get. It's like if you use these two different ansatz. Okay, so let me just stop here for now.